Hello everyone. Hello. Today we are going to start week 5 of MLF. So the first topic of week 5 is let's see some basic concept of complex numbers. So the complex number is represented by I. This is iota. Iota is under root of minus 1. So this is how you represent the complex number. It is iota. So and there are some properties of iota like if you say iota is under root of minus 1, then what is I square? I square is under root of minus 1 whole square, that will equal to minus 1. If you say I cube you can write it as I square into I, that is, what is I square? I square is minus 1 and into I, that is minus I. Same I raised to the power 4, I square into I square, so minus 1 into minus 1, that is 1. That's how you can find the value of I raised to the power 5, I raised to the power 27. Suppose you are having I raised to the power 28. Okay, no, not 28. Suppose we are having iota raised to the power 25. Divide this number by 4. So if iota raised to the power 4 times 6 plus 1. Okay, so this will be I raised to the power 4. You can say that 4n plus 1. So iota, wait, this will be iota raised to the power 4n plus 1. Here n is 6. So what is the multiple of 4 will be 1. So iota raised to the power 1 and okay. So iota raised to the power 4 will be 1. Uh, Same will be iota raised to the power 8 will be 1. Iota raised to the power 12 will be 1. Iota raised to the power 16 will also be 1. Iota raised to the power 20 will also be 1. Iota raised to the power 24 will also be 1. Here we need to find the iota raised to the power 25. So this can be written as 1 into iota, that will be iota. Okay. Oh, okay. So now there are some properties of complex numbers. Suppose, okay. So complex number is represented in the form of z is equal to a plus iota b. Okay. Here a is the real part and b is the b is also see b is also a real part, but here we are multiplying b with this iota. So after multiplying it with iota, it will become imaginary part. Okay. So this is some basic concepts of complex number which you will require in the week 5. Now the properties of complex numbers. First property is, suppose if you are adding two complex numbers, suppose first complex number is a plus iota b and second complex number is c plus iota d. Here you have to add real part with the real part and imaginary part with the imaginary part. So the output will be a plus c, both real parts, because a and c are the real parts, plus iota times b plus d. So you can say that the combination of real part plus imaginary part after addition. Okay. Next property is same goes with subtraction. A minus iota by oh wait, a plus iota b minus c plus iota d. Again you have to subtract the real part with real part, that is a minus c plus iota times b minus d. Okay. Yeah. And a plus iota b can also be written as r e raised to the power iota theta. Okay. And this e raised to the power iota theta can also be written as r into cos theta plus iota sin theta. Okay. Yeah. So I hope this is clear. Fourth one is, suppose if you need to find the length of the complex number, this will be r square is equal to a square plus b square. How? Suppose, let's add one more page. Suppose you are having a complex number a plus iota b. You need to find the mod of r. Then under root of a square plus iota b square. So under root of a square is plus, what is I square? So this will be I square b square. Okay. And mm, so I square, and this will be under root of a square plus b square. Okay. And if you say r square will be equal to a square plus b square. And same, that a plus iota b can be represented as r e raised to the power minus theta. If you want to represent a minus iota beta, then this will be r e raised to the power minus iota theta. Okay. Yes. So now comes conjugate. Conjugate of complex number. Conjugate of complex number is represented by bar. This is bar. Okay. So suppose if you are having a complex number as a minus a plus iota by, so suppose this is z. Okay. Now if you want to find conjugate of complex number, z bar is bar of a plus iota b. In this bar you have to change the sign of iota. Suppose if we are having a plus iota b, after like taking the conjugate of the complex number, this will come as a minus iota b. Here I have changed the sign of iota. Okay, suppose if you are having a complex number a minus iota b, then the z complex will be a plus iota b. Okay, when the conjugate, you have to do only one thing, that is change the sign of iota, and you will get your required answer. And generally the inner product is represented by x transpose y, and generally x transpose y is not equal to y transpose x. Keep this in mind. Okay. So there's a one property called commute. So if the product is AB and this is equal to BA, that means it is commutative. Oh wait, this is commute. Okay. Generally this is not possible. I hope this is clear. Now there are also some properties of conjugate. Properties of conjugate. Suppose a plus iota b, and you have to multiply it with c plus iota d. Okay, so you have to take the wait. So if let's multiply it with, so ac plus iota ad plus iota bc plus, this will be I into I square bd. Okay, so this will be minus 1, right? So I square is minus 1. So this will come as AC plus iota AD plus iota BC minus BD. So take the real numbers, A minus AC minus BD plus iota times AD plus BC. Now if I want to take the conjugate of the same, this will be bar, and here I will change the symbol of iota, that is AC minus BD. Here plus, here it is plus, so I will after changing it will return as minus iota AD plus BC. Okay. Same goes with addition. A plus iota B plus C plus iota D This will become as A plus C plus iota times B plus D. After taking the conjugate of the whole, I will change the sign of iota. It will become as AC, A plus C minus iota B plus D. Okay. Yeah. Now, and generally in terms, suppose if you are having a complex number A plus iota B, you will take A as R cos theta, B as R sin theta. Okay. So you will able to represent A plus iota B in terms as R cos theta plus iota R iota sin theta. If you take R common, you will get cos theta plus iota sin theta, and it will be equal to R e raised to the power iota theta. Okay. Now the next topic is length of complex number. Length of complex numbers. Suppose you are having a complex number in terms of vector as x1, x2 up to xn. So length is represented by mod, and this will be equal to x conjugate transpose into x. First you need to do the conjugate, then you have to take the transpose, then you have to multiply with the real vector. Okay. Suppose there is an example. We are having a complex number as 1 iota. You need to find the length of this complex number. So this will be equal to x conjugate y as x conjugate transpose into x. Okay. So what is the conjugate of this vector? You have to change the symbol of iota. So x conjugate will be equal to 1 and minus iota, and x bar x conjugate transpose will be equal to 1 minus iota and 1 iota. Okay. So this will be equal to 1 and minus I square. What is I square? I square is minus 1. So 1 in minus of minus 1 will be equal to 2. Okay. So this is how you have to find the length of the complex numbers. Then there are some remarks for the length. Suppose, and I have already told that generally x conjugate transpose y generally not equal to y conjugate transpose x. Okay. Second property is x dot y will be equal to y dot x only if the conjugate exists or not. So x dot y will be equal to conjugate of y dot x. Okay. Third property is x dot cy is equal to c into xy. Fourth property is cx dot y will be equal to c into x dot y. There are these are some properties which you have to keep in mind. Okay. Next topic is conjugate transpose. Okay. Conjugate transpose C. There is nothing special. Conjugate of transpose is represented by A star. So this star is basically A conjugate transpose, or you can do either first do the transpose of A, then do the conjugate. You can do both the ways. Okay. Either you take the conjugate of A vector, then do the transpose, or you can do that first. You can do the transpose of the vector, then do the conjugate. Okay. Now the remarks are, so I think maybe most of you do not know this property. Suppose if you are having a matrix A, B and you have to do the transpose of whole, so this will be equal to B transpose A transpose. Okay. Suppose if you are having A, B, C, then you have to do the transpose. This will be equal to C transpose B transpose A transpose. That is in the reverse order. And for the symmetric matrix, A transpose should be equal to A, and for skew symmetric matrix, A transpose should be equal to minus A. Okay, and same goes with here. Suppose if I want to take the conjugate transpose, then do the again conjugate transpose. This will return the original complex vector. And third one is um, this AB whole conjugate transpose. This will be equal to B conjugate transpose into A conjugate transpose. Same like this symmetric property. Okay. Now the next topic is inner product. See, inner product, it is same. Suppose x dot y will be equal to x conjugate transpose y is equal to x1 transpose y plus x2 conjugate y2 and up to xn conjugate transpose y. So generally for complex numbers, x dot y is equal to x conjugate transpose y. So that's how you have to find the inner product. Inner product is nothing but the you can say length of the complex numbers, and how you have to find the length is like this: x conjugate transpose into x. Okay, yeah. Now comes Hermitian matrix. See, just like symmetric matrix, what was symmetric matrix? That A transpose should be equal to A. For this Hermitian matrix, your A conjugate transpose should be equal to A. That's all. That means A conjugate transpose should be equal to A. Okay. A matrix is Hermitian if and only if A conjugate transpose is equal to A, and Hermitian matrix are equivalent to similar matrices in complete vector space. Okay. Now the properties of Hermitian matrix. Let's see some properties of Hermitian matrix. That if A is a Hermitian matrix, then the eigenvalues. You all remember how to find the eigenvalues? That is, determinant of A minus lambda I should be equal to 0, and here you have to find the lambda. Okay. And the eigenvalues of this Hermitian matrix, eigenvalues should be real. Okay. Next property is uh, this property is same as of eigenvalue and eigenvectors. That how you have to find the eigenvectors. AB is equal to lambda b. Okay. Now same for Hermitian matrix. Suppose Ax is equal to lambda x. A is a Hermitian matrix. Lambda is the eigenvectors and x are the lambda is the eigenvalue and x are the eigenvectors. Okay. Here x should not be equal to 0 and lambda should not be equal to 0. Okay. Now if you take the conjugate transpose of this whole, this will be equal to if you take the conjugate transpose on both sides, and then okay, so this will be equal to x conjugate transpose into A conjugate transpose. Okay, and this will be equal to lambda conjugate and x conjugate transpose. This is conjugate of lambda. and if you multiply x on both the sides, x conjugate transpose A. For A, so see, for Hermitian matrix, this A conjugate transpose is equal to A. So if I write A or A conjugate transpose, the meaning will be same. And if I write x there and lambda conjugate x conjugate transpose into x, okay. So you know that Ax is equal to lambda x from here, okay. So you can say that um, x conjugate transpose lambda x is equal to lambda conjugate x conjugate transpose into x, okay. This is the property. Okay, this is the property you have to keep in mind. Third property is all real symmetric matrices are Hermitian matrix. Okay. Fourth property is if no eigenvalues is repeated, then A is diagonalizable. You all remember how to find whether A is diagonalizable or not? A is equal to PD P inverse. Here A will be your Hermitian matrix, P will be your eigenvectors, D will be the diagonal matrix of your eigenvalues, and P inverse will be the inverse of your eigenvectors. Okay. Now the next property is, it is a quite important property for this week. Suppose if you are having two eigenvectors as Ax is equal to lambda 1x and Ay is equal to lambda 2y, where lambda 1 is not equal to lambda 2. Okay. Then the like the dot product of both the eigenvectors, or you can say the inner product of both the eigenvectors, will be orthogonal. That means if Ax equal to lambda 1x and Ay is equal to lambda 2y, where the eigenvalues are not equal, the inner product of both the eigenvectors will equal to 0. Okay. And the most important property is if x and y are orthogonal. Okay. It is linearly independent set. That means if the dot product of both x and y, or you can say the inner product of both x and y is orthogonal, then the set of x and y will be independent set. Okay. Hmm. Let me see if I have any questions regarding this. Yeah. Let's take the example. Suppose you have A matrix as 2, 3 minus 3 iota, 3 plus 3 iota, and 5. Okay. You need to find the, you can say the eigenvectors. So Ax, now you have to see the eigenvalues are 8 comma minus 1. How you will find? You will find by taking determinant of A minus lambda I equal to 0. Okay. Now A minus 8 I x, this will be equal to minus 6, 3 minus 3 iota, 3 plus 3 iota, and minus 3, and x1 x2 is equal to 0. Okay. This will give you leading to x as 1 and 1 plus iota. So this is your first eigenvector. Okay. Same A plus lambda A plus I into y, that will be equal to 3 3 minus 3 iota, 3 plus 3 iota 6, y1 y2 equal to 0. This will give you 1 minus iota and minus 1. Okay. Now according to property, the inner product of both the eigenvectors should be orthogonal. So 1 into 1 minus iota and 1 minus iota minus 1. This will be equal to 1 minus iota minus 1 and 1 minus iota and 1 minus iota. So 1 minus iota and plus iota square. So this will be minus 1. So this will be cancelled out and this will be minus 2 iota. Okay. And wait. The first eigenvectors was 1 and 1 plus iota. Okay. So the conjugate will be 1 and 1 minus iota. And y is 1 minus iota and minus 1. So the orthogonal is 0. Okay. Like the inner product of both the eigenvectors are orthogonal. So that this is how you will find the eigenvectors and you have to find the inner product. Okay. Now next topic is unitary matrix. Okay. So a matrix is unitary if and only if the matrix is a square matrix. That means n cross n matrix and columns should be orthonormal. That means length of the columns should be equal to 1. Okay. Now suppose if we are having two complex numbers x1 x2 and x conjugate transpose into x2, if it is equal and if it is square and columns are orthonormal, then it is unitary matrix. Okay. Now the properties of unitary matrix. That means the first property of unitary matrix is the length will be unchanged. Suppose ux, this will be equal to length of x. Okay. How this is possible? Suppose ux into uy. If you find the length, see how you will find the inner product. Ux conjugate transpose into uy. Okay. So this will be x conjugate transpose u conjugate transpose u into uy. This u conjugate transpose u will be you can say identity matrix. That means u conjugate transpose into u will be equal to 1. This will be equal to x conjugate transpose y. Okay. That means the length will be unchanged. Next property is eigenvalue of v has absolute value. Absolute value means mod of lambda is 1. Okay. Suppose ux is equal to lambda x, and as we all know that the length is unchanged. Sorry. So this ux, if I say lambda x equal to x, and this will be separated as mod of lambda x into mod of x is equal to mod of x. This will be cancelled out and mod of lambda will be equal to 1. Okay. Now, and for unitary matrix, for a Hermitian matrix, for a Hermitian matrix, A will be represented as U and U conjugate transpose. Okay, this will be your unitary matrix. This will be what? Diagonal matrix with eigenvalues, and this will be the conjugate transpose. Conjugate transpose. Okay. Next topic is Schur's theorem. Okay. Now, Schur's theorem, suppose if you're having an n cross n matrix, A is similar to an upper triangular matrix. Upper triangular matrix T. Okay. Yeah. So, upper triangular matrix T, that is exists an unitary matrix A is equal to UTU conjugate transpose. Okay. Here T will be your upper triangular matrix. Now, the final topic is spectral theorem. Okay. Now, this is spectral theorem is like, let's take another page. Spectral theorem. The spectral theorem states that any symmetric, or you can say Hermitian matrix, can be diagonalized. So here you have to do the diagonalization of a Hermitian matrix by an orthonormal basis of eigenvectors. Okay, this will be represented as A is equal to Q and Q transpose, where this will be your same diagonal matrix containing the eigenvalues of A. Okay, and Q consists of eigenvectors. Q consists of eigenvectors. So that was the theory of week 5. Okay, and these are the activity questions. Okay, see, the statement that the inner product of two complex numbers is always commutative. Commutative means what? The inner product of x conjugate transpose y should be equal to y conjugate transpose x. This is generally not equal to. That means this statement is false. Consider vector x1 belongs to r raised to power n and x2 belongs to c raised to power n. Which of the following computes the square? See, square of length means x1 conjugate transpose x1 and x2 conjugate transpose x2. So x1 conjugate transpose x1 and x2 conjugate transpose x2. This is the correct option. And x1 transpose x1 and x2 conjugate transpose x2. This is also correct. Okay. Given a complex matrix, the notation it is A star stands for conjugate transpose of conjugate A or conjugate of transpose A. You can do both the ways. These are the properties. A conjugate transpose raised to whole conjugate transpose will be equal to A, and A B whole conjugate transpose will be equal to B conjugate transpose into A conjugate transpose. And then, so the following properties are correct for complex vectors x and y. See, x dot y generally not equal to y dot x. So this is not the correct property. Then x dot y is equal to y dot x conjugate. So this is the correct property, and these two are also the correct properties. Okay. Here you have to find the conjugate transpose of A. See, first you need to find the conjugate. So 1 plus iota, 2 plus 3 iota, and minus 2 iota. After taking the conjugate transpose, this will be 1 plus iota, 2 plus 3 iota, and minus 2 iota. That means third option. Hermitian matrix is a complex vector space or generalization of symmetric matrix in a real vector space. Hermitian matrices are orthogonally diagonalizable if eigenvalues are distinct. Okay, this is also true because I have already mentioned in the video that where it is. If no eigenvalue is repeated, then A is diagonalizable. Okay, the diagonal and elements of Hermitian matrix are real. Yeah, true for all Hermitian matrix. Eigenvalues of Hermitian matrix are always real. The eigenvectors corresponding to distinct eigenvalues of an Hermitian matrix are orthogonal. That is also true. How? Ax is equal to lambda x and ay is equal to lambda y. So the x conjugate transpose y will be equal to 0. All real symmetric matrices are Hermitian. True. Matrix U is unitary if it is a square matrix and orthogonal columns. It is a square matrix and orthonormal columns. Okay, both are true. See, for two vectors to be orthonormal, they first have to be orthogonal. Okay, yeah. If U is unitary, then which of the following statements are true? U conjugate transpose will also be unitary. U into U conjugate transpose will be equal to I. How? See. I have mentioned here. U conjugate transpose U or U into U conjugate transpose will be equal to identity matrix. Columns of U forms a orthonormal set. This is also true. And so the option will be all of these. Eigenvectors corresponding to distinct eigenvalues of a unitary matrix are orthogonal, same as a Hermitian matrix. Every unitary matrix is a Hermitian matrix? False. But every Hermitian matrix is a unitary matrix. Every Hermitian matrix is a unitary matrix, but every unitary matrix is not a Hermitian matrix. Which of the following is true about eigenvalue lambda of a unitary matrix? That it has absolute value mod of lambda equal to 1. For a Hermitian matrix, we can find the unitary matrix, but for a unitary matrix, we cannot find a Hermitian matrix. As per the spectral theorem, any Hermitian matrix A is unitary diagonalizable. All Hermitian matrix A is unitarily diagonalizable. How? The spectral theorem states that any matrix A can be diagonalized using this property Q, and I don't know how to pronounce this. So this will be the eigenvectors of A and this will be the diagonal matrix of eigenvalues. Okay. The Schur's theorem, what is Schur's theorem? A into UT U transpose. Given ion cross and matrix, there exists a unitary matrix U and upper triangular matrix T such that A is equal to UT U conjugate transpose. For any Hermitian matrix A, the spectral theorem states that D is equal to this and U is unitary matrix and D is what? D is the diagonal matrix of your real entries. Every unitarily diagonalizable matrix is a Hermitian matrix. Now, every unitary matrix is not a Hermitian matrix, but every Hermitian matrix is a unitary diagonalizable matrix. Every Hermitian matrix is a unitary diagonalizable? True. Now, these are all the practice assignments. What is the first question? First question is simple. You have to find a complex conjugate. Okay, I'm not going to do this question. So the first question is you have to find this complex conjugate of this matrix. Second question also you have to find a complex conjugate. Third question is you have to find the inner product. How you will find the inner product? Inner product of s dot x dot y will be equal to x conjugate transpose y. Okay, so this will be equal to 1 plus iota minus 2 iota and 1 minus 1 minus iota and iota. This will be equal to minus of 1 plus iota whole square plus minus 2 iota into iota. So minus 1 plus 1 minus 2 iota plus 2. That is 2 minus 2 iota. So third option is correct. Square of length of vector x. I will find the square x. X conjugate transpose into x. So 2 plus iota, 4 plus iota into 2 minus iota and 4 minus iota. This will be equal to 22. So 22 is the correct answer. The matrix A is unitary or not? Yeah. So like the condition of A to be unitary is that its column must be orthogonal and orthonormal. So A1, A2. Suppose if I take the columns of matrix A will be A1 and A2 for checking the orthogonality. This will be 1 minus iota by root 3 and minus iota by root 3 into 1 plus iota by root 6 and 2 iota by root 6. So this will be equal to 4 by 3 root 2, that is not equal to 0. That means for a matrix to be unitary, the columns will be orthogonal and orthonormal both. But here is the inner product is not equal to 0. That means this matrix is false. Like this is not a unitary matrix. Okay. The matrix Z is Hermitian. So definition, what is the definition? Given matrix A is Hermitian if and only if the A conjugate transpose will be equal to A. Okay. So this you can say you can see that 1, 2, 3, 2, 4, 5 and 3, 5, 6. If you find the conjugate transpose, this will be 1, 2, 3, 2, 4, 5 and 3, 5, 6. That means this is equal to the real matrix. So this is the Hermitian matrix. Seventh question. Which of the following matrices are Hermitian? Okay. Again, you have to find whether the A conjugate transpose is equal to A or not. Okay. So the correct option will be this D. Okay. Now this eighth question, you have to find the eigenvalues of a matrix A. If you remember the property of eigenvalues and eigenvector, that the trace will be equal to sum of eigenvalues. What is the trace here? Trace is 3. Yeah, trace is 3. So minus 1, minus 6 and 2. The sum is minus 5. This is wrong. 1 minus 6 minus 5 minus 2. This is minus 3. Also wrong. And 1 plus 6 7, 7 plus 2 9. This is also wrong. 1 6 minus 1 5, 5 minus 2 is 3. So this is the correct answer. What is ninth question? Let A is equal to K. See, the process of finding these type of questions is, see, this is a unitary. That means the length of the columns should be equal to 1. Okay. If I take A1 and A2 as their columns, and if I say the inner product of A1 and A2 should be equal to 1. Okay. So if I multiply K inside, this will be K times 1 minus iota, 1 plus iota, and K times 1 plus iota and 1 minus iota. This will be equal to 4k square. Okay. Now 4k square should be equal to 1. So k square is equal to 1 by 4. That k is equal to 1 by 2. So 1 by 2 is the correct answer. Again, similar question. If the value of k is 1 by 2, you have to find this value of k. Okay. Again, 1 by 2 root k minus root k iota, 1 by 2 root k and root k iota. this will be equal to 1 by 4 k plus k, that is 2k by 4, that is k by 2. So k by 2 should be equal to 1. The value of k should be equal to 2. Okay. Now this 11th question is, let A is, you have given a matrix A. If A can be factorized as A is equal to U D U conjugate transpose, where U is denoting the unitary matrix and D is denoting the diagonal matrix, then U and D are. Okay. See, trace should be equal to the sum of eigenvalues. So trace is 5. This can be 2, this can be 2, this can be 2, but this is not the correct answer because the trace is minus 5. Okay. C is eliminated. Now you have to find the unitary matrix. What is U? U is the sum of, you can say, the group of your eigenvectors. So determinant of A minus lambda I, this is equal to 2 minus lambda 3 minus lambda minus of 2, that will be equal to lambda square minus 5 lambda plus 4. This will be equal to lambda square minus 4 lambda minus lambda plus 4. If you take lambda common, lambda minus 4 minus 1 here, lambda minus 4, then lambda minus 4 and lambda minus 1. So lambda should be equal to 1 comma 4. Okay. But options are here. So if you now see the eigenvalues are 1 comma 4. Now finding, see, for these type of questions you need to find, see, first put lambda equal to 1, then 1 1 plus iota, 1 minus iota, and 2. Okay. So for nullifying these type of questions, just remove the second row. Okay. So this will be 1 1 plus iota and 0 0. Okay. Now then, for finding the eigenvectors, multiply this with minus 1. Okay. So this will be your minus 1 minus iota and 1. So this is your first eigenvector. Again, for lambda is equal to 4, minus 2, 1 plus iota, 1 minus iota, and minus 1. Divide the first row by 2, minus 2. So this will be 1, minus 1 minus iota by 2, and again nullify the second row. This will be 0 0. Again multiply this with minus 1. So this will be 1 plus iota by 2 and 1. If you multiply again with 2, this will be 1 plus iota and 2. This is your second eigenvector. Okay. If you do not understand, let's revise this quickly. Put the value of lambda equal to 1 in the real matrix. Okay. Put the value of lambda into the real matrix. Then you will get this matrix. Okay. First step is nullify this. Nullify means remove this row from the matrix. So this will be 0 0. Okay. Then multiply with minus 1 into the iota part, that is imaginary part. So this will be your minus 1 minus iota, and paste this as same as it is. Okay. 1. Again put lambda is equal to 4. You will get minus 2 1 plus lambda 1 plus iota, 1 minus iota, and minus 1. Make this as 1. So if you divide the first row with minus 2, this will be 1 minus 1 minus iota by 2, 0 and 0. Okay. Then again multiply this imaginary part with minus 1. So this will be 1 plus iota by 2 and 1. So if you multiply again with 2, this will be 1 plus iota and 2. Now your eigenvectors are minus 1 minus iota by minus 1 minus iota, 1 1 plus iota and 2. If you normalize this will be your minus 1 minus iota by root 3, 1 by root 3, 1 plus iota by root 6, and 2 by root 6. Okay. If you check the option A will be your correct answer. Okay. This is a very confusing, you can say very confusing question, but again, let's revise again. Put the values of your eigenvalues simultaneously. You will get the some matrix. Remove the second row. multiply -1 to the imaginary part. This will be your first eigenvectors. -1 minus iota 1. Again, after putting lambda is equal to 4, you will get this matrix. Make this first element 1. So for making this first element 1, divide the first row with -2. This will be your 1, and -1 minus iota by 2, 0 and 0. Okay. Again, multiply the second element imaginary part with the -1. This will be your 1 plus iota by 2 and 1. Again, multiply with 2. This will be 1 plus iota and 2. Okay. And then normalize it. So this will be your correct answer. I hope this is clear to everyone. Then which of the following matrices are unitary? Again, for a matrix to be unitary, the column of the matrix must be pairwise orthogonal, or you can say the orthonormal. Again, you have to do the same, x conjugate transpose into x. Okay, this should be equal to 1 for a unitary matrix, and answer will be E option. Okay. Now let U and V be two symmetric matrices. Consider the following statements: UV is symmetric and U plus V is symmetric. Okay. So suppose AB transpose, this will be your equal to B transpose A transpose. If this AB and symmetric, that means A transpose should be equal to A and B transpose should be equal to B. So this A transpose and B transpose will be AB. So you can say AB transpose is AB. Okay. Similarly, if you say UV transpose, this will be equal to V transpose U transpose. And if these are symmetric, then this will be equal to UV. So that means this is symmetric. So both statements are true. See, U plus V is not symmetric. U plus V is not symmetric. Okay. U transpose plus V transpose. Okay. So sorry. Wait. See UV transpose. This will be equal to V transpose U transpose. So VU is equal to VU is equal to UV. So generally this is not possible in this complex numbers. Okay. So first statement is false. See, generally AB transpose is equal to AB. That is for real numbers. But here we are dealing with the complex numbers. So complex numbers, generally UV is not equal to VU, as we have already seen the commutative part. This part, commutative. X conjugate transpose Y is generally not equal to Y conjugate transpose X. Now, U plus V transpose is equal to U transpose plus V transpose. So this is equal to U plus V. So this is same, but there is no option for this to be true. So both statements are true. No. Both statements are false. No. Second is false. No. So your C will be your correct answer. That is C option. Okay. So that's all for week 5. I hope it is clear. Do the practice assignment, do the GA assignment, and do the PYQs for your upcoming quiz 2. Okay. So bye bye. Let's meet in the second video.